Okay, so let me get the sign-in sheet passed around. A couple things. So exam 1 has been graded and returned. I have the grades posted on Blackboard, but I haven't turned them on yet. So I'm going to turn them on sometime today. But everything is current on Blackboard except for your homework 4. That's still being graded. I mean, remember that homework was big, so that takes a little time. Now, homework 5 is due Wednesday, March 7th. I think after today and definitely after Friday, you'll have no problem tackling problem 4. But right now, you can do the rest of homework 5 right now. There's really nothing stopping you. A couple other things. I am not going to be here on Monday, March 5th, so I'll probably post a video introducing shear, because shear's coming next, and then we'll dig into that when we get back. Couple other announcements. I mentioned last time the Corps of Engineers is having a day here on Marshall's campus on March 6th on Tuesday from 10 to 2 in the Student Center. So if you have a chance to check that out and you're interested, you should. One other thing I thought I would mention is the ASHE North Central West Virginia Scholarship. I don't know, there was an email sent out about that I think yesterday. Did you all get that? Okay, the scholarship application is due Monday. Apparently, they haven't gotten as many applications as they normally have, so it's sort of like they're sort of pushing you to apply. But the application needs a reference letter. I'm happy to write one, but like I'm not going to be here Monday. So if you're going to do this, you kind of need to tell me like now. So.
Okay. How specific are they on the West Virginia resident, even if you're working in? I mean, I live in Chesapeake. Like.
I have no idea. I have. Okay. Okay. All right. Hold on. Okay. And which means I need to get your reference, like I can probably turn them around. I can probably turn them around tomorrow. Safer bet is Friday, but I need to know now. So here's what we're going to do. The sign-in sheet's going around. If you're going to do this, put on the sign-in sheet that you want to do it, and if you need a reference letter is basically what I'm asking. If you need a reference letter, let me know. If you didn't get a chance, we'll get your name on there before class is over. Does that sound good? So when y'all are done with the sign-in sheet, I guess get it back up front, and then if you're going to do this, we'll get you a reference letter. Is that all right? Any questions? Okay. All right. So today I want to get into the process for doubly reinforced beams. Doubly reinforced beams, I think you're going to find it's a natural extension of our lecture on T-beams. The topics, they're really different and really similar at the same time, because if you recall, with T-beams, we had sort of two cases for analysis. We had the case of whether or not we were dealing with a rectangular T-beam or a true T-beam. What was the difference? Like what's the difference between a rectangular T-beam and a true T-beam? Somebody. So, the stress block, right? If the stress block is either a rectangular shaped stress block or it's a T-shaped stress block. Likewise, with doubly reinforced beams, we're going to have a similar two cases of analysis, but they're going to be different. First off, I talked a little bit about this last time as to why you would even consider two layers of reinforcement. I don't really think you need to consider it so much from a design standpoint. I mean, by design, I mean like flexural capacity, like MN. In other words, if you have a beam, if you have a scenario where you need to design a beam, more often than not, you can probably design that beam for flexural capacity and not need to include compression steel. But there are some benefits to including it, specifically for long-term deflections. You kind of need to know how to account for it when you're doing beam column analysis, which is something we'll do like in April. That'll be near the end of the semester. Also, compression steel is usually there because you're tying together your rebar cage, so you usually have some rebar up top anyways. For now, we conservatively neglect it, but if you want to account for it, you can. Since it's present, there's really nothing stopping you, but you got to do it correctly. A couple things. So, and I say a couple things, we're going to talk about couples, forced couples. When we did T-beam analysis and we looked at the capacity of a true T-beam, if you recall, we basically split it up into two force couples, and we said the capacity of a true T-beam is computed by taking the flange steel couple and the web steel couple and adding them together. Well, when we look at doubly reinforced beams, we're going to do something very similar. We're basically going to take the couple between the concrete and steel, and then the couple between the two layers of steel. So the concrete and the tensile steel, and the compression steel and the tensile steel. In terms of notation, I think I mentioned this last time, but whenever you're looking at a beam that has compression steel, you're going to see a lot of primes pop up. For instance, the area of steel, A sub S versus A sub S prime. Instead of D, we have D prime. Anytime you see a prime on there, that is referencing a dimension or a quantity associated with compression steel. So you see here a layer of steel up top, that's AS prime, D prime. D's from the top, D primes from the top of the beam to compression steel. D's from the top to the tensile steel, and so on and so forth. So just make sure you're cognizant of the notation. One of the challenging, what really makes doubly reinforced beam analysis complicated is whether or not the compression steel has yielded. So if for T-beams, the complicated issue was where was A, did you have a rectangular T-beam or a true T-beam? For doubly reinforced sections, what makes it complicated is determining whether or not the compression steel has yielded. Now, let me show you something. Let's sort of take our time with this. Okay, first off, let's go over here and let's look at a stress-strain curve. So for analysis purposes, what we have done so far in this class and in reinforced concrete is we assume that our stress-strain curve for steel looks something about like this. It's either linear up until Fy or it plateaus, right? So this slope is the Young's modulus for steel, which is 29,000 KSI. That plateaus up here at Fy, and then there's that strain here, that epsilon sub y, that's the yield strain, right? And the yield strain is computed as Fy divided by ES. Like y'all remember that, right? That's not very a very big deal. Well, up until now, here's what's going to get interesting. Up until now, every single strain value that we've ever computed for steel has always been bigger than that, right? We've always had strains of like 0.005 or 0.004 or even something like 0.009 or 0.01. Like we've always blown through that for the tensile steel. But for the compression steel, that's more often than you would think not going to be the case. See, ACI states that the strain in tensile steel has to be greater than what? 0.004, right? And that limit basically was there to ensure that if you have tensile rebar, it's going to yield, okay? That's why that limit is there. But the key word is tensile. That limit is ensuring that tensile steel yields. Doesn't say anything about compressive steel. Compressive steel does not have to yield. It doesn't have to, okay? And you're going to find that the analysis is a little more intricate than you would think. Now, how do we determine whether or not compressive steel has yielded? We look at the strain, okay? So how do we compute the strain of steel in compression? Well, we have our strain profile, which looks something like this, right? Remember the maximum usable concrete strain we always use is 0.003? Y'all remember that? So remember this strain calculation, we use similar triangles, right? We said 0.003 is to C as whatever this value is to D minus C. And that's how we determine the strain at the bottom. But for the strain at the top, the formula is a little different. So for tensile steel, it was D minus C. It's backwards here. It's C minus D prime, and I'm going to show you why. So 0.003 is to C as whatever this value is to this distance. And what is that distance? Well, it's C minus D prime. Does that make sense? Everybody okay with that? So to compute the compressive steel strain, it's going to be this, okay? If that strain is larger than the yield strain, then it has yielded. If not, then we're dealing with stresses in this linear range right here. Does that make sense? Everybody with me so far? Okay. Now, what we're going to do is this. If the compression steel has yielded, then that compressive force is simply the area of steel times Fy, right? Same as we've been using before for the tensile steel, just ASFY. It's AS prime Fy because we're talking about the force and compression. If not, then it's a little more intricate. Let me go back to my stress block here, or not my stress block, my stress strain curve. Okay. That's my stress strain curve, right? Okay. So this strain value right here is epsilon sub y, right? This is Fy. Okay. So let's make up some numbers to make this make a little more sense. Let's say this is 0.00207, which is normally the yield strain for 60 KSI steel. Okay? Now, let's make up some numbers. Let's say that the strain in the compression steel is 0.003. If that's the case, what is the stress? It'd be just Fy, right? Because think, here's our yield strain, and if our stress is 0.003, that means it's over here, right? And if it's over here, that means the stress is Fy. Is everybody following along with me on that? Okay. Now, let's make up something else. Okay? Now let's say that our strain is something like this. Let's say it's that. Has our steel yielded in this instance? No, right? In fact, on the stress strain curve, we're probably somewhere about right there, right? Does that make sense? So how do we compute what that point is? Well, I propose we take the strain and just multiply it by E. Y equals mx plus b, right? The y-intercept b is 0. The slope m is the modulus of elasticity, and that's our x value. So just, there we go. So I propose that in this instance, the stress is that, right? Now, if you're really paying attention, how do we compute this? Well, it's 0.003 C minus D prime over C. Does that make sense? Everybody with me so far? Any questions? All right, okay. So the actual force, so that's how we would compute the stress. The only difference between this and this is how do we compute a force? Well, it's a stress times an area. So take all this, multiply it by the area, and bam, you get your force. So we got to be a little careful in our calculations to ensure that we're tracking everything appropriately. Now, if the compression steel hasn't yielded, then things get a little tricky, okay? Because how do we compute where our neutral axis is? Well, we always use equilibrium, right? Equilibrium states that all our compressive force has to equal all our tensile force, right? Everybody remember that? So our tensile force is just ASFY, okay? Well, what about our compressive force? Well, our compressive force, we have the compressive force in the concrete and the compressive force in the steel. Now let's take a look at this compressive force in the concrete. Look what I've got written here. I've got 0.85 FC prime beta 1C. How is that any different from 0.85 FC prime AB? What did I do? What is A? A is beta 1C, right? Remember that? Okay. This is from that previous slide, assuming the steel hasn't yielded. So if you multiply everything around, like if I multiply everything by C, that denominator cancels, I get a C over here, and this I get C squared, right? So if you expand everything, you end up getting this, this nice little quadratic equation you have to solve for to determine where your neutral axis is. That's if the steel has not yielded. I know that you're like, oh goodness. Don't worry, I promise when you actually start grunting through it, it's really not that bad. And plus, everybody in here has their Casio FX115 ES Plus, right? That will solve quadratic equations like that. So don't worry. If you're thinking this is a lot, we got plenty of practice coming up, so it ain't going to be so bad. Speaking of practice, let's look at a couple examples. So I have two doubly reinforced beam examples. If you've been paying attention, one of these, the steel is going to yield. One of it, the steel isn't going to yield, you know, because I'm a pretty predictable guy. But I think you're gonna see how this is pretty straightforward. Actually, the beams themselves are very similar. The dimensions are all the same. The only thing that changes is the rebar and some of the material parameters. But I think you'll see that this isn't so bad. Okay, so what I have here is I have a beam that is doubly reinforced. Now notice this, okay? Notice how I've got D from the top to the tensile steel is 24 inches, but D prime is from the top to the compression steel, and that's only 2.5, okay? So make sure you're understanding the difference in the dimensions. And notice how I've got an AS and an AS prime, 2 square inches for the compression steel and 6.25 square inches for the tensile steel. Just make sure that you're aware of that, okay? I'm going to copy this onto my notebook over here, so, oh goodness, every time. There's got to be a way of like changing that setting, because okay. Example 11A. Now, what was FC prime for this example is 3 KSI. What does that mean? I'm just curious. Everybody paying attention. What's beta 1? 0.85. Remember, it's 0.85 for anything less than 4K, or less than or equal to 4 KSI. And FY is 60. Okay. Now, if FY is 60, and whenever you're doing a doubly reinforced beam, the very first calculation that you should do right off the bat, if you don't already have the value, is compute this. Because this is going to be how you determine whether or not your assumptions are correct. So remember, write out those units. Take your pen or your pencil, write that little K, that little S, and that little I. Write them out, okay? So what are the units for this calculation going to be when it's all said and done? There are none. There we go. There were some strains in PSI on the exam. I'm like, don't know where that's coming from, but you got to write it out. All right, what do we got here? Yeah. Okay. So just keep that number in the back of your head, because we're going to refer to it here in a second. Okay? So far, so good? Now, in order to do this analysis, we have to make a guess right off the bat. Okay? The guess I'm going to make is that the compression steel yields. Okay? I'm doing that because That's the simpler approach. But we're going to check that assumption here in a second. So let's assume compression steel yields. Again, we have to check this, but you'll see us do that here in a second. So compression equals tension, right? So our compressive force, now in our example, there are two compressive forces. There's a compressive force in the concrete plus a compressive force in the steel. That's got to equal whatever our tensile force is, okay? Sound good? Okay. All right. Good question. So anytime you see a prime, I'm talking about the steel up top. Anytime that you don't see a prime, I'm talking about the steel at the bottom. So, and that's sort of a simple way of distinguishing which one you're talking about. So if you see like a row versus a row prime, you know that the row prime is always talking about the compression steel. That's a good question. Anybody else? Any other questions? If you ever see a beam and there's pre-stressing elements in it, you'll always see like a sub P. It's like a D sub P, a rho sub P, A sub PS, and it's talking about the area of your pre-stressing strand. So it's just a simple way of making sure that you're keeping everything in track. So it's a good question. So far, so good? All right. So let's go ahead and define these terms. Now, for the concrete, what we're going to do is we're going to say 0.85 FC prime AB plus, now for the compressive steel, what I'm going to do is I'm going to say the area of steel times Fy. Now, technically we are kind of doubling up on the area a bit because in reality, the area of concrete and compression would technically be whatever this shaded area is minus the area due to rebar. But because of the scale, I mean, if you wanted to be, technical about it, you could, but it really doesn't affect things very much in the end for beam columns or for beams. So we sort of neglect it and just say 0.85 FC prime AB. We do take that into account for columns, but that'll be a little bit of a bigger discussion later because the reinforcement ratios are a little bit bigger. So we'll deal with that later on when we talk about columns. So we are sort of doubling up on our area, but no big deal. For tensile steel, we're saying area of steel times Fy. Did everybody understand what I meant when I said doubling up on area? Because if I say 0.85 FC prime AB, well, there's steel there, but there's not a lot of steel when you compare the whole size of that stress block. So it's pretty straightforward. So far, so good? So let's make this simple. What do we need to solve for right now? A. So how do I do that? Take this, subtract it over, take that and divide, right? So notice how there's a common Fy. So what I'm going to do is this. I'm going to say A equals, whoop.
We don't immediately plug in theta 1, 2 there.
Not yet. We're going to do that here in a second. You can if you want to save yourself some time, but I'm just taking it one step at a time. So AS minus AS prime times Fy over 0.85 FC prime B. Does that make sense? Did I go too fast with that? Now, I know some of the math purists in here are going, well, wait, there's a subtraction in there. Could you get a negative answer for A? Analytically, you could. Practically, you never would. Because what that would mean is you'd have to have more compression steel than you would tensile steel, and that ignores a fundamental principle about concrete. Concrete is a material that behaves very poorly in tension. It would never make sense to have a beam where you'd have more tensile steel than you would compression steel. So mathematically, yeah, you could get a negative answer, but practically it would never make sense. So just thought I'd throw that out there. All right, so 6.25 square inches minus 2 square inches, 60 KSI, and then 0.85 4 KSI. No, this is 3. This is 3. And then, what was B? 14 inches. So what does this come out to be? 7.143? Something like that? Okay, and while we're at it, let's go ahead and compute C. And that comes out to be what? Like 0.403? Okay. So far, so good? All right. Where are you from? Okay. Any questions? Now, here's what I'm going to do. Let's go ahead and let's compute the strain in the steel, but specifically the strain in the compression steel. So that is 0.003, and it's C minus D prime over C. So 0.003, 8.403 inches minus 2.5 inches over 8.403 inches. Now, what does that come out to be? 0.00211. Okay? Do I have a second on that value? Second. Somebody tell me what that means. It's larger than what? Exactly. It's larger than the yield strain. But now what does that mean? It means the steel is yielded. So our assumption is correct, right? What if it wasn't correct? Well, it would mean two things. Number one, all this is wrong. And two, means that Dr. Mike ought to have another example on that problem. I do. It's example 11B. I got this. No, we're going to have our next example. We're going to have one where the steel doesn't yield. Okay, so right here, epsilon sub s prime is greater than or equal to epsilon sub y. That is bad. I could do better than that. So our assumption is valid. All right. And while I'm at it, let me go ahead and box all of this. And I'm doing that because if it was invalid, everything in that box would be wrong. Everything. Well, I guess that would be right, but how we computed that would be all wrong. So. Okay. Now, since I'm in a strain-happy mood, let's go ahead and compute the strain in the tensile steel, so 0.003. And here what we've got is D minus C over C. So the subtraction reverses because we're on the opposite side of our axis, and we're using D because we're looking at tensile steel, not compressive steel. So 0.003, 24 inches minus 8.403, 8.403 is what? Second on that? Tell me what that means. There's two observations we can make about that. So B is 0.9 because it's greater than 0.005. And also, it's greater than 0.004. So it meets the minimum. Bless you. Is everybody okay with this? Any questions? Okay. Let's see. I think we can get through this. So I got one thing I want to do. We're not going to finish the problem, but I got one thing I do want to check. And I want to check equilibrium. How do I compute the compressive force in the concrete? It's 0.85 FC prime AB, right? So 0.85 3 KSI times what? And B is 14 inches. Now remember, A probably has a lot of decimals going after it. Yeah, so basically like 255 kips. I have a second on that? How do I compute the compressive force in the compressive steel? Area of steel times Fy. And remember, the only reason that we can use Fy here is because our assumption was valid. So that's 2 square inches. Let me put that decimal point there. Oh, come on. I think I can do that one in my head and I get 120 kips. All right. What is the tensile force? It's ASFY, right? So that is what, 6 square inches? 0.25. There we go. Yep. And what are we getting for this? Does that pass the equilibrium smell test? It does, right? All the compressive force is 375, that's 375. That might have seemed like a waste of time for this problem, and you could argue that it kind of was because A was pretty easy to compute. However, for 11B and for examples where the compression steel does not yield, you really need to do this in order to check. Now we are not done with this example because we have not computed MN, okay? Or phi MN, that is. We're going to do phi MN on Friday, and then Friday we're going to do 11B where the example is a little more intricate and a little more involved. So Friday is going to be chock full of calculations. All right, we'll see y'all on Friday. And again, sign-in sheet. If you are going to do this, this scholarship application, let me know, and if you need a reference letter, I can get you one. If you don't need one, that's fine. Just I need to know, and I kind of need to know now. So.